it has not been recognized so far that conservation of energy can be violated in classical physics on a macroscopic level. Such possibilities are demonstrated here for the first time. Shown below in some more detail is an instance of disobeying conservation of energy. When alternating voltage is applied to a resistor and a capacitor connected in series, the violation of energy conservation observed here is due to two asymmetries inherent in the theory of electricity between current and voltage in such system. The first asymmetry, inherent in the theory of electricity, concerns the phase difference between current and voltage due to the presence of capacitor, causing the relationship between voltage and current to no longer obey Ohm's law. Current now is first-time derivative of voltage. To make things simple, we'll illustrate the sinusoidal voltage applied to the RC circuit by sine t, and the current resulting from this voltage by its time derivative, cosine t. For simplicity, we'll consider the resistance R as negligible. Just as in almost any standard text, the current is leading the voltage and the phase shift phi is 90 degrees. This mutual disposition of current and voltage can also be demonstrated in an actual laboratory experiment with an oscilloscope. The fact that due to the presence of capacitor, current is first derivative of voltage, leads to the second asymmetry inherent in the theory of electricity, namely, voltage with any added constant voltage offset invokes the same current without offset. The constant voltage offset has no contribution to the current. These two inherent asymmetries combined, whose importance for the power balance has not been recognized thus far, determine the conditions in electrical systems for disobeying conservation of energy, with its far-reaching consequences. Observe first voltage with no offset, which standard texts usually discuss. Here, the integral of the voltage times current over the entire period, comprising the input energy throughout this period, is 0. Respectively, the quotient of that input energy and the period, comprising the average input power, is also 0. The physical meaning of this result is cited in the standard texts as a proof that conservation of energy is obeyed in electrical systems. That is, within the period, energy is given to the capacitor twice, in the first and third quarter of the period, resulting in capacitor acquiring energy of electric field. That energy of electric field is returned also twice within the period, in the second and fourth quarter, in exactly the same quantities as the energy put in. Unrecognized so far is that the physical picture regarding conservation of energy changes when a constant voltage offset is added to the sinusoidal voltage. Superficially, it may appear that the average input power for the period is to be calculated by a similar integral, summing up the instantaneous products of voltage and current, and then dividing this integral by the period. This integral would yield 0 as well, and one may conclude incorrectly that conservation of energy is also valid when there is constant offset added to the sinusoidal voltage. Observe, however, that most voltage values used to calculate momentary input power contain a constant voltage offset part, which gives rise to no current. That is, gives rise to no power. Therefore, inclusion of such non-power invoking voltage deforms the calculated momentary power value, making it incorrect. Just as an illustration, imagine there is a large constant voltage offset, F, applied to capacitor. Aside for the initial current of charging, long time ago, there will be no current flowing through capacitor. Therefore, no power will be input throughout the time F is applied. When a voltage ripple is invoked, causing current, it should be obvious that the input power is only due to the voltage of the undulation. The input power is only due to the wave. The underlying part of the voltage is not participating in the formation of the input power. We now detach the power-producing pattern of the voltage, just to show that it is no more related to the offset in the way it appears on the screen of the oscilloscope. The home of that power-producing pattern of the voltage is elsewhere. Of course, its home must be somewhere on the x-axis, because, as seen, it's the momentary values of the voltage wiggling around an axis that are the values which matter for the calculation of power. The x-axis, which is at the zero of the y-axis, provides the best reference level. To know the true values of voltage which are to be used for the input power calculation, current producing pattern of voltage is either one of the two broken curves. Notably, they produce the same current. Trivially, the current-producing and the power-producing patterns of voltage overlap each other for voltage which has no offset. Remarkably, for voltage with offset, the current-producing pattern and the power-producing pattern of the voltage do not overlap each other, because of the specific but physically correct way the constant voltage offset is to be eliminated from the instantaneous voltage values when voltage has offset, so that these instantaneous voltage values become appropriate for correct input power calculation in the instances when voltage has offset. But where exactly on the x-axis must the power-producing pattern of the voltage, which is derived from the voltage with offset, be positioned? Indeed, once we understand that voltage offset has no contribution to power, and therefore must be eliminated from the instantaneous values of voltage seen on the screen of the oscilloscope, so that these corrected voltage values can be used for correct calculation of input power, the crucial question becomes how this elimination of the menacing constant voltage offset is really to be done. One obvious, although wrong proposal, may be to eliminate the offset of the voltage by just bringing the voltage trace vertically downwards, back to its non-offset reference position. It is immediately evident, however, that this way of eliminating offset ignores the physical fact that at time t0 the capacitor has an actual non-zero voltage, capital F, applied to it. In other words, if this way of eliminating offset is adopted, the initial point, circled in red, of the offset voltage will not belong to the time-varying part of the actually applied voltage anymore. However, it must belong only the product of the current at time t0 by the actual non-zero voltage applied at time t0 gives the correct power value. Indeed, it should go without saying that the real voltage value, where point circled in red is positioned, should be used in calculating the power, and the only thing necessary is to somehow remove offset for the rest of the wavy curve, the only trace which can both possibly retain the pattern of time-varying part of voltage, while at the same time lose its constant offset, and have the point circled in red belong to it, is the non-offset voltage trace shown. This new, power-producing voltage curve is phase-shifted with respect to the original voltage trace, shown with the broken line. In this illustration, one sees clearly why the power-producing pattern of the voltage, derived from the voltage curve with offset, and shown with the red solid line, is phase-shifted with respect to the original no-offset voltage curve, shown with the broken line. Obviously, the offset provides a substantial advantage, because at t equals 0, it already ensures the level of charging of capacitor, which for the voltage curve without offset occurs later in time, requiring energy input to reach the same level of charging. It should be appreciated that offset ensures the fortunate circumstance that the capacitor is already charged as early as time t0. That charge is served on a platter earlier than it would be acquired if the charging has started from an uncharged capacitor. Once the capacitor being already charged at time t0, the further voltage curve will proceed, having the same shape as the shape of the curve that started from uncharged capacitor. That shape which proceeds from the already charged level at t0 will be built earlier than the same curve for the uncharged capacitor. Notice the phase-shifted voltage trace, comprising the power-producing pattern of the voltage, following from the voltage curve with offset, is not voltage which current is derived from. Shown phase-shifted voltage trace only provides the correct voltage values, which the corresponding values of current must be multiplied by, so that correct input power values can be obtained, in consideration of the fact that the applied voltage has offset. Therefore, if the actually applied voltage is 0.5 plus sine of t, that voltage must be changed, in accordance with what was just said, to sine of t plus pi over 6, in order for the power to be calculated correctly through integration. Therefore, if input power is to be calculated correctly when voltage has offset, the corrected mutual disposition of current and voltage is to be as shown here. Instead of mere voltage shifted to eliminate the offset, correct calculation of input power requires that the wave with offset is represented by the same wave without offset but phase shifted. The offset 0.5 is replaced by change of sign argument t. Similar are the arguments in the case when the voltage offset is negative. Notice, the phase shifting of voltage is done only to have the correct momentary products of V times I, and does not mean that a discrepancy in the timing of the current and voltage is introduced. Under the integral, the phase shifting of the voltage only transports the correct voltage value, mindful of its offset, to coincide properly with the current. In other words, in the long run, offset translates as a phase shift of the non-offset voltage when calculating power correctly. Here, we see an amazing fact. The input power has a negative value. This means that output power has been produced at no expense of input power. All the power from the generator being returned back to it. This is the ultimate violation of conservation of energy. When power I squared R on the resistor of the RC circuit is produced by saving of all of the input power, all of the input power being even returned to the generator. The generator causes the RC circuit to become a power source returning power, negative IV. At the same time, power of the amount of I squared R is produced in the RC circuit. This is power dissipated on its active resistor, denoted by capital R. Notice, once the broken line border is crossed, any power available is set to participate in the power balance. No power on the left of the broken line has any bearing on the power balance discussed. A mechanical analog of disobeying energy conservation, as a result of favorable juxtaposition of stationary fields, is provided by the magnetic propulsor. In it, a metal sphere lifted from level A to level B increases its gravitational potential energy minus the decrease of its magnetic potential energy. Should the conservation of energy be obeyed, the steel sphere should go back spontaneously, directly from B to A when let go, thus disposing of the exact amount of energy imparted to it. Experiment shows, however, an entirely different behavior of the steel sphere. When let go, the sphere proceeds along the rail surrounded by two permanent magnets. then reaches point C, and falls back to its initial position A. In going spontaneously from B back to A, along this longer path, through C, the steel sphere disposes of energy, which it finds itself possessing at B. That energy is greater than the energy imparted to it when lifting it from A to B. As seen, output energy is greater than input energy, and that is exactly what constitutes violation of conservation of energy. Although, calculation of input power is more exact by using integrals, as we've done here. Not the least because in this way input power of more complex signals can be calculated. Usually, for simplicity, standard texts calculate the average input power of sinusoidal signals by calculating the root mean square values, RMS values, of the voltage and current, and multiply that product by the cosine of the natural phase shift phi between voltage and current. In view of what was discussed herein, the correct calculation of input power using RMS values must be done by multiplying the product of these RMS voltage and current values by the cosine of a phase shift phi prime, different from the natural phase shift phi, as explained earlier. In another presentation, violation of energy conservation will be presented when electrolysis of water is carried out in an undivided electrochemical cell. This is the most important, unaccounted so far, effect in the widely discussed phenomenon known as cold fusion. Although ideologically, every example of violation of conservation of energy is equally significant. Conservation of energy violation in electrical circuits, discussed above, seems to be of especially great importance because it does not involve moving parts or messy chemicals. It also ensures, as said, the ultimate violation of energy conservation, allowing to produce energy without any energy input whatsoever. In view of its importance, we will emphasize several points, which, although should go without saying, sometimes may be a point of confusion. The power balance of concern for the conservation of energy is only regarding the circuit to the right of the broken line. It cannot be emphasized more strongly that the power necessary to run the pulse generator does not participate in the balance of power when conservation of energy regarding an electric circuit is examined. Thus, in order to prove violation of energy conservation, it is not necessary to demonstrate a self-sustaining device. That is, device running solely due to the excess energy produced during its action. The big novelty in the discussed way of producing energy is that the energy produced in the way discovered here does not come at the expense of depleting of a previously existing energy reservoir. This is not an alternative source of energy as it is understood nowadays, involving solar, wind, and other energies, which utilize already existing energy by converting from an already existing form into a form to be used for some concrete practical purposes. The discussed energy is not even alternative in the sense Tesla implies the term, because in Tesla's proposals, the energy produced, in no matter how exotic a way according to contemporary science, is still energy from a previously existing energy reservoir. The energy obtained according to this discovery, alternatively called excess energy or quote, energy out of nothing, unquote, does not come about at the expense of a pre-existing, already existing energy reservoir. Excess energy in this discovery is produced as a result of saving from the input energy due to so far unrecognized favorable juxtaposition and interaction of real elements and factors, other than already available energy. Thus, the phrase quote, production of energy out of nothing, unquote, is only a figure of speech. It is only a way of expressing that there is no pre-existing energy reservoir, but it does not mean that there are no other existing real non-energy components and factors, and their respective interactions, which are due to the approach described herein. In their totality, they allow for the production of energy, despite the absence of such energy prior to commencing the process. As already said, the method is based on utilizing natural asymmetries, so far unrecognized for quote, production of energy out of nothing, unquote, which exist in standard classical physics, and concretely here. In the classical theory of electricity, it should also be strongly emphasized that input power in electrical circuits, such as the one discussed here, is never measured directly. What is measured directly are two non-power, non-energy quantities, namely, voltage and current, which are then subjected to mathematical calculation to obtain input power. Input power in circuits at hand is only obtained indirectly, through calculation. The fact that electric power in such circuits is never measured directly, but is always determined indirectly, through calculation, makes the method of calculation crucial for the validity of power determination in electrical systems at hand. Also, the fact that power in circuits, such as the one observed, is always calculated from the direct measuring of two non-power, non-energy quantities, namely, current and voltage, and is never measured directly, has a crucial bearing on the ruminations about the practical applications of the new phenomenon discussed here, especially when, as is the case here, involving reactive elements, there is no immediately obvious energy equivalent, such as evolved joule heat, readily observed on active, dissipative elements, that might serve as a measure for the produced electric power. Thus, the experimental proof for the reality of the above discovery consists in the correct experimental determination of voltage and current and their correct mathematical handling, described herewith. As for the equivalent expression of the above produced energy through other kinds of energy, that is a question of future studies. The results presented above show for the first time a hitherto unrecognized possibility for violating conservation of energy in electrical systems. Violation of conservation of energy in mechanical systems, as well as in electrochemical systems, is demonstrated in more detail elsewhere. All demonstrated possibilities to violate conservation of energy make it impossible to consider the principle of energy conservation as a universal principle anymore. This discovery of the so far unrecognized inherent possibility to violate conservation of energy opens unforeseen, far-reaching perspectives for the building of principally new energy generators, as well as an ideological change in all of science. It changes the way science views energy. Such ideological change is probably of even greater importance than the pure utilitarian applications of the discovery at hand. It frees science from the artificially imposed limitations and strangulations set forth by the requirement to think of energy as something predetermined. The discovery discussed causes a complete overhaul of the simplistic way science perceives energy and distinguishes it from quantities which are necessarily conserved, such as a given mass of a given unique, single body in a given system, or the absoluteness of time. Uniqueness of mass, absoluteness of time, as well as other problems, explicitly or implicitly disregarded in contemporary physics, will also be discussed elsewhere.